Right.
We can handle them as we go, I think.
There you
that's
go.
hopefully been effective.
And that's efficient because so they also, I will share both the recordings and chat output. And chat typically has a lot of good information, the links that were shared and so forth. So I will share all of that as an information. All right, so I will proceed then. This is just addition to the 3-dimensional simulation. So let me now share my screen. All right, so this is just extension of the 3D visualization, and it's surface visualization. So again, what we exemplified initially was the volume and also surface as a height above the slice. In 3 dimensions, we might have, if you look at the surface of my head, it's a much more complicated surface that is not, it cannot be viewed as some sort of functional relationship of the plane, okay, below the head. So I need sort of like the information of how this surface is changing in space. And that's typically called isosurfaces. I have slides, which we don't have time for, that basically cover the basics of the algorithms that are trying to strike a plane through certain value of the data that you have in a 3-dimensional image. Okay, that's called in 2D contouring and in 3D isosurfaces. Okay, now in this particular case, we're going to actually use segmented data. Data doesn't have to be segmented. But segmented data is already decided, like what are the phases in the image, what are the specific components of the image that we're interested in. They're labeled in a much more simplified way than the grayscale data would be. Okay? So in that sense, I'm also not going to cover too much about segmented images other than say, well, they're also 3D images. And they just have a very simple set of values, 0, 1, 0, 1, 2, 0 and 255. So set of discrete values, and those values like 0 or 1 or 2 have specific meaning. They're labeled for specific mineral or fluid phase if we are actually talking about subsurface applications in porous media, but could be something else in a different type of image. All of this really applies to, I was talking about my head, to brain image. Okay, brain image is also a 3-dimensional MRI image typically. I might have different tissues within, so then I would label different tissues, or hopefully not, but a tumor within the tissue would have different density, and we would typically see it clearly shown. So in different applications of image visualization, we are looking for different things, but they typically come down to similar type of data types. All right, so I have in this cell, I have just sped up the download of the file that we already showed, as well as the statistics, just to be able to quickly check on it. And then I'm going to download a Ketten limestone blob. Here is the segmented data set, and you will actually see here a slice through it and all of the information that you need for its reading. And again, I remind you that if you download the file, the direct link will show up, or you can directly download it and then load it into your Python. So I'm not going to belabor that point. Here's how it's done. You need to do it once. It's also in the shared folder, just in case you don't want to download it now. It takes about 10 seconds on my computer, so it's not terrible, but it could get a little too long, in which case you don't want to do this multiple times. I need to read again the data from the website. This is this metadata that travels on Digital Rocks portal. This is actually the point of Digital Rocks portal, because this type of information is not often embedded in the binary files when it's created. So you have to know it, and that's part of the value of Digital Rocks portal. So this is the width, height, and slices. And these are unsigned, unsigned 1-byte integers. So this is the data type. This is another way to actually refer to it, just an alternative. And we read it in. So now let's say this surfaces, it's actually an algorithm, and it's a straightforward type of algorithm, but if it's actually working on the data on the fly, and there's a lot of data, especially in porous media, there's a lot of surfaces. That's actually one feature of the porous materials. Okay? If we actually use them in chemical engineering, that's why they're there for, because they have a lot of surface and there's a lot of reactions going on those surfaces. Okay? So a lot of surface will result in very large surface files. Surface typically are basically three-dimensional surfaces that delineate two phases in the image, or the value like below and above certain value in a tomographic image. So I chose to rescale the image before I do that here, just to make it a little more doable. Though this particular image is not too bad on my computer, but again, just to show it as an example, because this will be useful. So here, I actually first read in and I first plot original image statistics just to make sure what is in the image. It should be zeros, ones, and twos, and that's actually what says on the website. So I had to read a little bit on the website. Okay? And then after that, I rescale it. This is where actually there's a hefty comment here, but if I actually just did a dumb rescaling with these values, there's a problem, and what comes back is just floating point values, because that's what Sky Image does. It loves returning floating point values, and they're all scaled to some 0-1 range that makes no sense, and that's not where my data is. So I don't want that done in scientific visualization, so I have to take a little bit of care, and I have to provide floating point values and also tell it to preserve range. Otherwise, it's going to mess with it. So that's something to be mindful of. Okay, image rescaled is basically I'm just halving it, so making it half times smaller. And I'm going to plot the statistics again to make sure that I didn't mess with the data range. So when I actually execute that, we will see that my original, this is its shape, this is its type, and it's between 1 and 3 with this mean. Okay. And this is the half smaller size. You can see that the type has changed, and it's 64-bit floating point. Okay? And while floating points, we have numerical errors in storing the floating points. So 1 is now this, but that's close enough. 3 is now this, that's close enough. And then the very similar mean. Okay. And that's what I'm looking for, that I didn't change the range big time. All right, now we can actually show a slice through this image, and I can actually interact with it. Okay, so this is one specific slice, and I can actually walk through it. So I'm holding down, I'm working on my mouse on my laptop. I'm holding down one side of that mouse, and you can see this is my blob, the black, it's an oil blob inside Keton limestone. Limestone is in white. Okay, so this is walking through these slices. Okay, all right. Now, if I just want to plot the, so let me see. You can see, okay, holding down. Okay. So if I hold down, I can see this blob, okay, as an object in 3D. I would like to show it in 3D. This is right now just walking through the slices. It's not real 3D, okay? So I want to show the shape of that blob. So this is where I need to find the surface between that black space and everything else. Now my data tells me, or on the data, on the website, that oil is labeled as 1 in that image, that segmented image. Brine is 2, rock is 3. So between 1 and everything else, the value is 1.5. So I want to strive for 1.5 surface, isosurface, or also sometimes called contour in 3D. Contour is really a two-dimensional image, two-dimensional feature. So three-dimensional version of it is contour 3D, okay, or surface contour. Okay, so this interpolated value of 1.5 separates oil from everything else. Okay, and then the second piece is that I want to visualize is the image between rock and pore space. And since rock is 3 and oil and brine, that's 5 value is right in between those. So if I plot another surface at the value of 2.5, I'll be able to show basically the surface between pores and grains interpolated. Okay, so that's what we want to do. Okay, so let's now just, and this is now just setting up the certain details of the figure, and the CLF actually clears it from any previous plots. And I'm just now gonna put just one contour where oil is, basically that separates oil from everything else. I'm going to give it a color map and no opacity. So it should be, opacity is 1, so there's no transparency. Opacity and transparency are 2 different things. Here we go. And this is my oil blob. Woo. All right. Whoops. Okay. And now you can spruce this up, add the axis to it and so forth. If you go to that second Python notebook, there are some ways how you add the axis to the surface in one of the plots that James showed. I'm not going to do that right now. You can also interact with it right here and change colors and legends, change the surface and so forth in Maya V itself. Okay. So this is just for your information. You can also look at the projection, X from the bottom, Y from the top, Y from the bottom, Z. So those are projections onto the coordinate planes. Okay, cool. Now, just one last thing that we're going to add, and we're actually almost on time here, is to plot oil blob and grain surface together. So I'm going to put 2 contours. I'm going to also make them, I'm going to set opacity close to 0. Opacity and transparency are 1 over each other. So that there's going to be see-through, so I can actually see, so that things don't occlude each other. Okay. So let's actually do that. Might need to close this one now. There we go. Gonna take, so it takes a moment to produce that image, and the larger it is, the longer it takes. So now you can actually see the pore grain surface, which is this transparent yellow in this particular color map that I chose. And inside of it, you see a lodged blob. Scientifically, this is trapped phase of oil inside of the pore space. You're disconnected from it. It's a residual, so it's good luck getting to it and taking it out. And if it's really either oil or in environmental applications, you need to clean up non-aqueous phases, then it's hard to clean up because it's disconnected from the rest. Okay, that because there's a lot of study, it also blocks the flow of water. So in terms of relative permeability through the space, it acts as a block and disproportionately reduces the mobility of water through. And the mobility of oil in this case is 0, like it cannot move, or relative permeability to oil is 0 because it's disconnected in this particular image. So from the flow perspective, there's a lot of studies of these, how these phases, fluid phases sit in pore space, and there's a lot of related imagery on the portal. And I just want to show you that actually what's shown here, okay, is on the website, is it 214, I think, project? I think, we'll see now. No. Oh no, that's the previous one. Which one is it? 125, here we go. This is very close to, just to a different angle to this visualization right here. Yeah. Okay. So this is a short summary of things that we wanted to introduce and how to actually get your hands on the data inside of Python if you wanted to change it. We will now give it away to sponsors. We're gonna have, let's have a 5-minute break just to give everybody some space to breathe. And then we will give it away to sponsors to actually show you how to interactively do things much more quickly and efficiently that we've shown here. And that's both ends of this are useful because you need to know your data. Okay? So that way you have a good overview of what can be done with different types of resources. Everybody